We just looked at what the compiler is supposed to do. Now let's very briefly look at how this gets accomplished. And I'm going to give no details. There's a giant pile of code in the book that gives all the details. But what I want to do is just show you the essential idea here. Worry about the details some other time. Let's imagine that we're compiling an expression that looks like there's some operator and there are two arguments. Now what's the code that the compiler should generate? Well, first of all, it should recursively go off and compile the operator. So it says, I'll compile the operator, and where I'm going to need that is to be in the function register eventually. So I'll compile some instructions that'll compile the operator and end up with the result in the function register. The next thing it's going to do, another piece, is to say, well, I have to compile the first argument, so it calls itself recursively. And let's say the result will go into val. And then what it's going to need to do is start setting up the argument list. So it'll say assign to argle const fetch, so it generates this literal instruction, fetch a val onto empty list. Okay. However, it might have to work. When it gets here, it's going to need the environment. It's going to need whatever environment was here in order to do this evaluation of the first argument. So it has to ensure that the compilation of this operand, or it has to protect the function register against whatever might happen in the compilation of this operand. So it puts a note here and says, oh, this piece should be done preserving the environment register. Similarly here, after it gets done compiling the first operand, it's going to say, I better compile, I'm going to need to know the environment for the second operand. So it puts a little note here saying, yeah, this is also done preserving env. All right, now it goes on and says, well, the next chunk of code is the one that's going to compile the second argument, and let's say it'll compile it with a targeted to val, as they say. And then it'll generate the literal instruction building up the argument list. So it'll say assign to argle const of the new value it just got onto the old argument list. However, in order to have the old argument list, it better have arranged that the argument list didn't get trashed by whatever happened in here. So it puts a little note here and says, oh, well, this has to be done preserving argle. Right now it's got the argument list set up, and it's all ready to go to apply dispatch, which generates this literal instruction. because now it's got the arguments in argle and the operator in fun. But wait, it's only got the operator in fun if it had ensured that this block of code didn't trash what was in the function register. So it puts a little note here and says, oh yes, all this stuff here had better be done preserving the function register. Okay, so that's the little, so when it starts sticking, so basically what the compiler does is append a whole bunch of code sequences. See, what it's got in it is little primitive pieces of things, like how to look up a symbol, how to do a conditional. Those are all little pieces of things, and then it appends them together in this sort of discipline. So the basic means of combining things is to append two code sequences. That's what's going on here. And it's a little bit tricky. The idea is that it appends two code sequences, taking care to preserve a register. So the actual append operation looks like this. What it wants to do is say if, here's what it means to append two code sequences. So if sequence 1 needs register, I should change this, append sequence 1 to sequence 2, preserving some register. Yeah. We say and, so it's clear that sequence 1 comes first. So if sequence 2 needs the register and sequence 1 modifies the register, then the instructions that the compiler spits out are save the register. Right, here's the code. You generate this code, save the register, and then you put out the recursively compiled stuff for sequence 1, and then you restore the register, and then you put out the recursively compiled stuff for sequence 2. Right, that's in the case where you need to do it. Sequence 2 actually needs the register, and sequence 1 actually clobbers it. Right, so that's sort of if. Otherwise, all you spit out is sequence 1 followed by sequence 2. Right, so that's the basic operation for sticking together these bits of code fragments, these bits of instructions, into a sequence. And you see, from this point of view, the difference between the interpreter and the compiler, in some sense, is that where the compiler has these preserving nodes and says, maybe I'll actually generate the saves and restores and maybe I won't, the interpreter, being maximally pessimistic, always has a save and restore here. That's the essential difference. Okay? Well, in order to do this, of course, the compiler needs some theory of what code sequences need and modify registers. So the tiny little fragments that you put in, like the basic primitive code fragments, say what are the operations that you do when you look up a variable? Right? What are the sequence of things that you do when you compile a constant or apply a function? Those have little notations in there about what they need and what they modify. So the bottom level data structures, well, say this, a code sequence to the compiler looks like this. It has the actual sequence of instructions, and then along with it there's the set of registers modified, and then there's the set of registers needed. So that's the information the compiler has that it draws on in order to be able to do this operation. And where do those come from? Well, those come from, you might expect, for the very primitive ones, we're going to put them in by hand. And then when we combine two sequences, we'll figure out what these things should be. So, for example, a very primitive one, let's see, how about doing a register assignment? So a primitive sequence might say, oh, its code fragment, its code instruction is assigned to R1, fetch of R2. So this is an example. That might be an example of a sequence of instructions. And along with that, it'll say, oh, what I need to remember is that that modifies R1 and that it needs R2. Right, so when you're first building this compiler, you put in little fragments of stuff like that. And now, when it combines two sequences, right, if I'm going to combine, let's say, sequence 1 that modifies a bunch of registers M1 and needs a bunch of registers N1, and I'm going to combine that with sequence 2 that modifies a bunch of registers M2 and needs a bunch of registers N2, then, well, we can reason it out. The new code fragment, sequence 1 and followed by sequence 2, well, what's it going to modify? The things that it'll modify are the things that are modified either by sequence 1 or sequence 2. So the union of these two sets are what the new thing modifies. And then you say, well, what is this? What registers is it going to need? It's going to need the things that are, first of all, needed by sequence 1. So what it needs is sequence 1. And then, well, not quite all of the ones that are needed by sequence 2. What it needs are the ones that are needed by sequence 2 that have not been set up by sequence 1. So it's sort of the union of the things that sequence 2 needs minus the ones that sequence 1 modifies, because it worries about setting them up. Right, so there's the basic structure of the compiler. The way you do register optimizations is you have some strategies for what needs to be preserved. That depends on a data structure. Well, it depends on the operation of what it means to put things together, preserving something. That depends on knowing what registers are needed and modified by these code fragments. That depends on having little data structures which say a code sequence is the actual instructions, what they modify and what they need. That comes from, at the primitive level, building it in. And there's all, at the primitive level, it's going to be completely obvious what something needs and modifies. Plus, this particular way that says when I build up bigger ones, here's how I generate the new set of registers modified and the new set of registers needed. And that's the whole, well, I shouldn't say that's the whole thing. That's the whole thing except for about 30 pages of details in the book. But it is a perfectly usable rudimentary compiler. Let me kind of show you what it does. Suppose we start out with recursive factorial. And these slides are going to be much too small to read. I just want to flash through the code and show you about how much it is. Right, that starts out with, here's a first block of it, where it compiles a procedure entry and does a bunch of assignments. And this thing is basically up through the part where it sets up to do the predicate and test whether the predicate's true. The second part is what results in the recursive call to fact of n minus 1. And this last part is coming back from that and then taking care of the constant case. So that's about how much code it would produce for factorial. We could make this compiler much, much better, of course. The main way we could make it better is to allow the compiler to make any assumptions at all about what happens when you call a procedure. So this compiler, for instance, doesn't even know, say, that multiplication is something that could be coded in line. Instead, it sets up this whole mechanism. It goes to apply dispatch. That's a tremendous waste, because what you do every time you go to apply dispatch is you have to const up this argument list, because it's a very general thing you're going to. In any real compiler, of course, you're going to have registers for holding arguments, and you're going to start preserving and saving the way you use those registers, similar to the same strategy here. So that's probably the very main way that this particular compiler in the book could be fixed. There are other things like looking up variable values and making more efficient primitive operations and all sorts of things. Essentially, a good Lisp compiler can absorb an arbitrary amount of effort. And probably one of the reasons that Lisp is slow with compared to languages like Fortran is that if you look over history at the amount of effort that's gone into building Lisp compilers, it's nowhere near the amount of effort that's gone into Fortran compilers. And maybe that's something that'll change over the next couple of years. Okay, let's break. Questions?
One of the very first classes, I don't know if it was during class or after class, you showed me the say add addition has a primitive that we don't see, ampersand add or something like that. Is that because if you're doing inline code, you'd want to just do it for two? You can just do it for two operands. But if you had more operands, you'd want to do something special.
Yeah, you're looking at in the actual scheme implementation. There's a plus, and a plus is some operator. And then if you go look inside the code for plus, you see something called, I forget, ampersand plus or something like that. And what's going on there is that particular kind of optimization, because see, general plus takes an arbitrary number of arguments. So the most general plus says, oh, if I have an argument list, I'd better const it up in some list and then figure out how many there were, something like that. That's terribly inefficient, especially since most of the time you're probably adding two numbers. You don't want to really have to const this argument list. So what you'd like to do is build the code for plus with a bunch of entries. So most of what it's doing is the same. However, there might be a special entry that you'd go to if you knew there are only two arguments. And those you'll put in registers. They won't be in an argument list, and you won't have to const. And that's how a lot of these things work. Okay, let's take a break.